So some results that arrive from our factor theorem and remainder theorem. If we know we have k distinct zeros, let's say a1, a2 up to ak. Now each one of those I can substitute into the factor theorem and show that x minus that was a factor. Therefore, I must have a factor with all of those multiplied together. That's all it's really saying. So if you knew that 1 was a factor, x minus 1 is a factor, x minus 2 is a factor, x minus 3 is a factor, therefore what we get when we multiply x minus 1 times x minus 2 times x minus 3 must be a factor. Exactly the same as numbers if you think about it. I mean, if you've got a number and you know 2's a factor and 3's a factor, then you know 6 goes into it, because 2 times 3 is 6. Same idea. So alright, we're going to show that 1 and negative 2 are both factors of this, and then go and factorise our polynomial. So polynomial 1, yep, that turns out to be 0. Polynomial negative 2, yes, that also turns out to be 0. So we know x minus 1 times x plus 2 is a factor. There's our polynomial to factorise. But you'll notice, rather than writing our factor down as x minus 1, x plus 2, I've expanded it out. That's going to make it easier to work out the other factor, because I can still use the idea then of, well, leading term times leading term must give leading term. So we must have x squared in the second one. The constant times the constant must give me the constant. So I must have plus 5 in the other one. All right, well, we've got several choices now. I could go for how many x's do we have? How many x squareds do we have? How many x cubes do we have? If I go for how many x's, at this stage it says 5x, and 5x is what we want. I always feel uncomfortable when that happens, so I might double check with something else. So let's have a look at the x squareds. If I was to expand it out now, I'd have 5x squared minus 2x squared, which is 3x squared. So, okay, seems to be still working. Let's just check x cubed, just in case. How are we going to get x cubed? Well, there's only one way you can get x cubed there. X squared times x, and that gives me x cubed. Yep. Seems to work. So there's our complete factorisation, because, of course, x squared plus 5 doesn't factorise. Well, not using real numbers anyway, but that's what we're playing with at the moment as real numbers. Okay. So if our polynomial is of degree n, and we know n factors, or n zeros, then essentially we've got the polynomial. Because you cannot have more linear factors than the degree. It would be impossible. Because just say you did. Just say you had a quadratic, and for some insane reason someone's told you that, hey, x minus 1's a factor, x minus 2's a factor, x minus 3's a factor. But if you were to expand that out, you get x cubed. Well, that's not possible. So you can't have more linear factors than the actual degree of the polynomial itself. And that's what this one's saying. A polynomial of degree n can't have more than n zeros. All right, so we're told our polynomial has a double zero at negative 7 and a single zero at 2. Write down a possible, and what they're really meaning here is a general polynomial that covers everything. Well, I know x minus 2 is a factor. X plus 7 squared is a factor. What else could happen here? It could be times another polynomial. But that other polynomial can't have 2 or negative 0, can't have 2 or negative 7 as a 0. Because if it did, say it had another 0 at 2, then we wouldn't have a single 0. Now it would become a double 0. So whatever that other quadratic is, it can't have a solution of 2 or negative 7. I could have a multiple of the whole thing. Now whether I really need that k or not, because that quadratic over there could have a multiple of k in it anyway. But it's possible it could be times some number. If we restrict it a bit and say, hey, we want a monic polynomial of degree 3. Well, I know x minus 2 is a factor. I know x plus 7 squared is a factor. I can't do anything more because it's degree 3. so I'm not allowed to have another factor. It's monic, so I can't multiply it by a number. So there's only one possibility in this case, and that is x minus 2, x plus 7 squared. If it was monic of degree 4, so there's the two factors that I know, but it could be times another factor to make it degree 4. But a couldn't be 2 or negative 7 for the same reason. It would change the, what's called the multiplicity. So it would change the degree of the factor. A polynomial of degree 5. Okay, I've got to multiply it by a quadratic. Notice I wrote it down as qx. I did not write it down as, say, x minus a times x minus b. Because to write it that way, I would be assuming that that quadratic could be factorised. It might not be able to be factorised. So that's why I've just written it as times a polynomial of degree 2. And again, that polynomial can't have a solution at 2 or negative 7. It didn't specify monic, so I could multiply it by some number as well. And this is where I now contradict myself. Remember, I just said you cannot have more zeros than the degree. So if you do have more zeros, which I just said you can't, then there's only one thing that your polynomial could be, and it's what we call the zero polynomial. It's a weird polynomial. And there it is. Polynomial x is just simply equal to 0. Now 0 is a polynomial. It satisfies all the rules. But what's its degree? It can't have a degree. Because we said the degree was the power of the leading term. It doesn't have a leading term, because the other thing we said about a leading term was that the coefficient can't equal 0. So it's this really weird polynomial. Watch out for that little question where you start overthinking it, but as soon as they tell you that a polynomial has got more solutions than the actual power of the polynomial itself, you must be talking about the zero polynomial. It's the only solution that you could have. Using the congruent symbol instead of the equal symbol. So if you see that, what they're saying is the two polynomials are identically equal. So if you were to draw both of them, they would fit on top of each other. It means, therefore, it is the same polynomial, so all the coefficients must be equal. So if you had a1x to the n plus b1x to the n minus 1 plus c1x to the n minus 2 and so on and so on and so on, is the same polynomial as a2x to the n plus b2x to the n minus 1 and so on and so on and so on, then the coefficients are equal. So you know a1 must be a2, b1 must be b2, c1 must be c2, and so on and so on. So that's the sort of question where if you're told that you've got these two quadratics and they're equal for, say, 3 values, then you know they're the same quadratic. So therefore, zero polynomial is another way of thinking about it, but the coefficients must be the same. Okay,